using the mathematical induction to prove this formula. We are claiming that 1 times 1 factorial plus 2 times 2 factorial plus dot 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 up to n times n factorial is equal to n plus 1 factorial and then minus 1. And this is true for all positive integers n. So induction is, here we go, PF by induction. And let's do the happy case, which is the base case. And the base case is when n is equal to 1. So on the left-hand side, we just have 1 times 1 factorial, and that's just equal to 1, and that's very nice. Okay, I'm just going to do like this. And on the right-hand side, if I plug in 1 into here, then we get, actually, I'm just going to put like 1 times 1 factorial to match the n and n here. And then I'll plug in 1 here, which is equal to 1 plus 1 factorial that, and then minus 1, which is 2 factorial, which is 2. Minus 1 is, of course, equal to 1. So this right here checks. That's the base case. If you do this on the test or something, you can get like 1 question out of 10, right? That's the case. Anyways, now, inductive hypothesis. Here, I'm just going to say, assume the claim is true for n is equal to some k. What this means is that I can legitimately plug in k into here and then make it true. So that means, i.e., that is 1 times 1 factorial plus 2 times 2 factorial, so on, so on, so on, and then plus k times k factorial. This is nicely equal to n plus 1, and n is k now, and then factorial that, and then minus 1. And that is what we can use later on. And then, from the inductive hypothesis, we will have to show that the formula is also true for n is equal to k plus 1. So we'll check that. Check n is equal to k plus 1. And to do this, I'm just going to be plugging k plus 1 to the left-hand side. So we will have 1 times 1 factorial plus 2 times 2 factorial plus dot dot dot. And then I know plugging k plus 1 in here and here, right? But I would also like to write down its term before it, which is n times n factorial, sorry, k, because I'm using k here, k. That's a horrible k, right here. And then plus, here we have the k plus 1, and then k plus 1 factorial. There. Okay, the good thing about this is that all of these things right here up to the k, this, by the inductive hypothesis, we know we can replace that with that. So this is equal to just k plus 1 factorial and then minus 1. And I'll just say by IH. And then let's write this down. Plus k plus 1 times k plus 1 factorial. Now this is very nice. What can we do next though? Now notice we have the k plus 1 factorial in common, so we can factor that out. Do the algebra for this. So we have the k plus 1 factorial. And then we still have a 1 right here. Keep that in mind. And then minus, actually no, the minus 1 is later on. I'm just going to have the plus k plus 2. And then the minus 1 goes all the way here. Because first term, second term, and then third term, the minus 1 here. Oh, sorry. This right here should be k plus 1. I jump ahead a little bit because that's exactly k plus 2. Okay, so I'm just going to write it like this. This is k plus 1 factorial times this is k plus 2, and then minus 1. K plus 2 times k plus 1 factorial. This is precisely k plus 2 factorial minus 1, which it's pretty much this right here already. And depends on how you like your inductive. It depends on how you like to write your induction proof. I personally like to purposely write this as k plus 1 and then plus 1 and then factorial minus 1. because this is super clear that we are plugging k plus 1 into the n and n here, and also this n here, and by induction, this formula is true. That's it.